Now the integral over a region of space, often we use d for this. I did in the last example. R could be confused with the notation we often use for the real line, although that's usually written a little bit differently. In any case, over a volume region. The integral of the divergence of f over a volume region is just like an integral of density. Divergence of f is the density of flux, essentially, or the density of divergence, let's say. So that the integral over the bounding surface of f dot n ds, as we maybe saw in the last example, is generally kind of a pain. We've got to mess with the surface increment, or the area increment of the surface. We've got to fool around with the normal vector. Doing the dot product usually isn't a problem if we know the normal vector and we can, if we know our function f. But this is generally kind of a painful integral and often ends up just plain old impossible to integrate. These are actually two unrelated statements, just two observations. We treat this just like an integral of density, and we note that the integral over the surface is often a kind of a painful integral, not always. Let's take an example. The integral over the surface of this function dotted with n over the surface, where s is the paraboloid z equals 16 minus x squared minus y squared, with z greater than or equal to 0, plus, remember, the surface has to be closed in order to apply the divergence theorem. So we're going to also have to take the disk x squared plus y squared less than or equal to 16, where z equals 0. Quick little picture. Our paraboloid is going to basically look something like this. Comes out in the x direction back here. It's going to have circular cross sections, and it's going to be bounded then by the disk x squared plus y squared equals 16. The circle x squared plus y squared equals 16 down in the xy plane, and we've got to include both the paraboloid and that disk, which is kind of hidden by the paraboloid, the disk in the xy plane that closes the figure. The paraboloid itself is open when you get down there. We've got to close it, we've got to put the cap on it, and that's the disk x squared plus y squared less than or equal to 16. Okay? Now, for this situation, our normal vector, well, we have a normal vector for the paraboloid, we have a normal vector for the disk that kind of caps the end of it. For the paraboloid, the normal vector is just the gradient of this function, of actually what we get if we add x squared plus y squared to both sides. We get x squared plus y squared plus z equals 16, making this a level curve of z plus x squared plus y squared. So the normal vector is this. That's the normal vector for the paraboloid. For the disk, it's easier. The normal vector to the disk, which lies in the xy plane, is either k or negative k, and it's negative k that points out of this region, so that the normal vector will be negative k. The area increment for the paraboloid is easily verified to be 1 plus 4x squared plus 4y squared. Recall we get that by just doing the normal vector dotted with k divided by the magnitude of the normal vector. The magnitude of the normal vector is 1 plus the square of 2y plus the square of 2x, which is this. We're dividing our dA by the dot product divided by the magnitude, and that gives us this. I'm not going to go through those details again here. But it's easy to write that down. And ds is just equal to dA for the disk because the disk is already in its own plane. Now remember, we're trying to evaluate this integral. If we try to evaluate it directly, we've got to go through these steps. And the result is going to be this. The circle in the xy plane has the parameterization that leads you to the limits on the integral. Very straightforward. Yeah. The f dot n is easily enough written down. We have our f function, which I haven't really written. F is, well, actually, yeah, we have x is 2xi plus y squared xj plus yzk. If we dot that with our normal vector, we get 4x squared and 2y cubed x and yz. And that's exactly, I think, what I've written down here. Multiplying by our ds, which is, again, our angle factor, our 1 over cosine of gamma times our dy dx. This is the integral over the parabolic part, and then we have the integral over the disk. And writing that down pretty much without comment, because that's going to give you 0. The function, our f of xy dot n for the disk, is just going to be yz, negative yz, and z equals 0, so that this whole thing is going to be 0 here. Still, this is sort of a painful integral. Our alternative, we can simply write the expression for the divergence and integrate this over the entire volume region, where z goes from 0 up to the paraboloid. Y and x have the are described by the inequalities that give us these limits on the integral, and that's very straightforward and should be familiar by now. And this integral is not nearly as painful as this integral. The worst thing you get into here is integrating powers of 16 minus x squared, essentially. Again, we can apply the divergence theorem because the volume implicit in the description of this region is enclosed by the surface that we've used to set up these integrals. Now, if we really want to know what this integral is over the paraboloid, having done this integral, we can say, well, our previous result gave us this integral if we complete the details of integrating the expression that I left you with. That's going to equal the integral over the paraboloid plus the integral over the disk of the normal component with respect to the surface area. It turns out that this one was easy to evaluate, and that, in fact, it was 0, but maybe in some cases it wouldn't be 0. It's still going to be a much easier integral because it's an integral over a disk in the xy plane. Normal vector is negative k, and if the f function didn't contain a factor z, this would be a non-zero result. But we could still get the integral over the paraboloid by doing the easier integral of the divergence and subtracting the easier integral over the disk. So this is easy. This is easy. This is not so easy, but equal to what we get over here. And that's actually kind of slick.